I'm now recording again. We're trying to get this class together. We've had some speed bumps today. Okay, but it seems as though things are looking good. My work is legible now, and we can continue our discussion. So here I was just kind of discussing this particular problem. I forget who had who brought this up, but does this kind of help in terms of what I'm asking for from proofs?
Yes, it does.
Perfect.
Yeah.
Any other questions that I can help y'all with today? Feels like today is a day where I just, don't rush with our lecture and just talk to y'all about math.
That's honestly like the best kind of teaching, where you're not just like lecturing, you're just conversing with us.
That's what I try. We'll see how it goes. So, no other questions on this particular aspect of sets or proofs? If not, then let's do another example, because I think these examples are good. So let's show the following. I forget if I gave this as a homework problem or not. So let A and B be subsets of U. Let's show that A is a subset of B if and only if the complement of B is a subset of the complement of A. Did I assign this for homework? Oh, I did. Well, that's fine. I still like this problem. If I assign it on homework, then that means that y'all already know how to do it. So how should I begin? Yeah, exactly. I need to split this into two parts. One thing that I need to do is I need to prove that A is less than or equal to B implies that the complement of B is contained inside the complement of A, and then the second part will be the other direction, right? So I need two directions. So this is part one. Okay, so what do I need to show to prove this? I need to show that whenever this holds, this must hold as well, right? So we assume that A is a subset of B. And then I want to show that this holds. So let X be an element of B bar. What does that mean?
Why the arrow has 2 lines?
Instead of 1?
Yeah.
No, not really.
Okay, I just wanted to be sure.
I think I actually might. Actually, maybe yes. I use this for implications, and I'll use arrows like this and like this for functions, which we might get to today. But yeah, so the double line, I suppose, can mean implication. Okay, so what does it mean if X is inside the complement of B?
That X isn't in B.
Right, thus X is not in B. Could X possibly be in A?
No.
Right, since since A is a subset of B, we see X is not in A. Thus, X is inside A bar. So we see by our assumption, we can show that this is true. So A subset B implies B bar is a subset of A bar. Now we can go in the other direction. First, we assume that the complement of B Yes, the symbol could also mean closure. The complement of B being contained in the complement of A, we want to show that this implies A is a subset of B. Okay, so we assume, again, if I'm trying to prove an implication, I assume the beginning, and I show that the conclusion must hold. So we assume that B complement is contained in A complement. Great. Now let X be in A. What should my next step be?
Can you say that since X is in A and A is a subset of B, that X is then in B?
So on this stage, I do not know that A is a subset of B. In fact, I'm trying to prove that A is a subset of B. So these two steps must be taken as like totally separate.
Oh, okay, I see.
Right, I'm proving both sides of the implication. So currently, all that I know is that the complement of B is contained inside the complement of A. Right, in this case, thus, since X is in A, X cannot be inside A complement. That's true. Since, so yeah, right. Since B complement is a subset of A complement, we see that X cannot be in B complement, right? X is not in this set, and this is a subset of this, so X can't be in the subset. But what does it mean if X is not in B complement? Yeah. So X is in B. What I showed is I assume the hypothesis, then I need to show that the conclusion is true. To show that the conclusion is true, I'm trying to show that there's a subset. So I take an arbitrary element of the smaller thing, and then I have to show that it's in B. So I took an element in A. I had to translate it into this sort of language so I could use this information. X being in A means X is not in A complement, so it's not inside B complement, so it's inside B. Thus, X being inside A implies X is inside B. Thus, B complement being contained inside A complement implies A is a subset of B, and we're done with the proof. So now everyone's going to get that problem perfect on the homework, which is good. I'll just let Sarah know not to grade that one. Any questions on this? No? We're happy with this?
I do have one question.
Sure.
So how do you get from saying that X is an element of, like in the second part of the proof, saying that X is an element of B, how does that conclude that A is a subset of B?
Right. So to prove an implication, I'm proving that if this is true, then this must be true, right? And when is A subset of B true?
When all the elements of A are in B?
Right. A subset of B is true if for all A in A is in B. So what I took is I took an arbitrary element of A, and then I showed that it had to be an element of B as well.
Okay,
Thus,
cool, that
this
makes
statement
sense.
is true. Oh, sorry, you can't see very well. Good questions. Any other questions? Can I show that A set minus B is a subset of A? Sure. Is this another homework question? So prove that, yeah, okay. Prove that A set minus B is a subset of A. Okay, so let X be inside A set minus B. What is the definition of this set?
By definition, X is in A, not B.
Yes, by definition, X is in A and X is not in B. Precisely. And now by simplification, X is in A. Thus, I've proven that it's a subset. Yep, this one's not so rough. Breaking it down, like here's some very general advice that holds, and I hope that I have demonstrated this, but it's good to kind of say it out loud. Every time that I'm starting with some expression like this, you should just write down in the margins or in your notes, what is the definition of the sets involved? What does it mean when X is in A set minus B? Well, it's precisely that X is in A and X is not in B. You can always break it down into these very simple logical connectives, and then that'll show you the way forward. Yeah, so this one's pretty short, or it can be pretty short. Still, good questions. And good answers, and good knowing of the definitions of A set minus B. Any further questions? No further questions, that's okay. Okay, would you rather that I did some examples of some complicated unions and intersections, kind of like Sarah did, or should I move on to functions? And y'all are already happy with kind of complicated unions and intersections.
I think some examples would be helpful.
Will do. So perhaps this is just a brief note that I can recall. We can consider very general unions and intersections. And Sarah did go over this, right? At least mention some quite general, like unioning up n sets, or unioning up an infinite collection of sets, or intersecting an infinite collection of sets.
Yeah, she did it with like the big U or whatever.
Yeah, exactly. Okay, so we're just going to do some more examples. Hopefully they're not exactly ones that Sarah did. So let's consider the following 4 problems. Let's take the union of the AI when I is equal to 1 up to infinity. And let's also consider the intersection of the AI when I is equal to 1 all the way up to infinity of the following sets. First of all, when AI is equal to the interval in the reals from 0 to I. Okay. So how do we think about, say, the first one? Let's consider the infinite union of all sets of this form. Well, the first thing that I would do is draw some pictures, right? here's the real line. Here's 0. The first, here's 1, here's 2, etc. 3. What is A1?
Zero to one, not inclusive.
That's right. It's just these. 0 to 1, this is A1. A2 is this interval. A3 is this interval. And so on and so forth. So my next question is there any positive number that is going to escape being inside one of these AIs?
Zero?
That's true, yes. 0 will escape because 0 is not in any of the AIs, but what about any number larger than 0? No, those will never escape, right? The higher numbers will never escape because I can always find an integer that is like at least 2 greater than any given number. Thus, the union of these AIs is equal to the interval from 0 to infinity. And this notation, infinity isn't a number, but this notation means all reals greater than 0, right? This is the union of all of these AIs. What about the intersection of all of these AIs?
Wouldn't that be zero? Since they all like intersect at 0?
Well, none of these sets actually contain 0, right?
Would it be just like A of one?
Yes, the intersection of all these sets, the intersection of the AI from I is equal to 1 all the way up to infinity is going to be precisely equal to A1, because every single set strictly contains A1. Right? For instance, if I'm considering like 0 up to 1 intersect 0 up to 2, what is this intersection?
0 to 1.
Yeah, this is just 0 to 1. What if I intersect it with 0 to 3? Well,
Still 0 to 1.
exactly. Since all of these intervals contain A1, and right, that's the way to think about this particular problem. All of these intervals AI strictly contain A1. So I know that A1 has to be inside the whole intersection. And moreover, anything outside of A1 cannot be in the whole intersection because it's not in A1. And the intersection means it has to be present in every single one of these sets. So here, the intersection of all of these is precisely A1. Here's the union. Any questions on these? Let me do another example. This one, how about this? Let's do the intersection from I is equal to 1 all the way up to infinity of the interval -1 over I to 1 over I. Was this one that Sarah did? If it is one that she did, then I have a different option. Okay. But what's the answer for this one, by the way?
Would it just be A of 1 again?
So here, I'm not working with the sets AI. I'm working with these intervals, which are going between -1 to 1, and then it's like -1/2 to 1/2, et cetera, et cetera. So it's actually not going to be the So Mahita, actually, you're correct the first time. This massive intersection is not going to be empty because there is an element that is contained inside each of these subsets. This is actually the set containing 0. This set is not empty because there is an element which is inside every single interval, right? If I'm considering like the picture here is something like this. Here's 0, here's 1, here's -1, here's -1/2, here's 1/2, here's a third, here's -1/3, etc. So I'm considering first this whole interval, then this smaller interval, then this smaller interval. For any integer that I put in the denominator, 0 is going to appear, right? Because these are going to be little parentheses clustered around 0. Do we agree that for any I, 0 is inside this set? Right. So 0 is going to be inside all of these sets. However, given any x not equal to 0, what do we know? If I have an x not equal to 0, what's some fact that I can use? So here's my picture. Here's 0, here's x, which is pretty close to 0. The statement is that I can find, oh, sorry, is someone going to say something?
No, sorry. You're good.
Given any x not equal to 0, there exists an n inside z such that 1 over n is less than x. I can always find a fraction of the form 1 over some really huge number that's smaller than x. I can always find some massive, like, I don't know, 10 bajillion. If x is some reasonably small number, 1 over 10 bajillion is probably smaller than that. Okay, and then this means that x is not inside the interval -1 over n up to 1 over n. So given any non-zero number, I can always exclude it by finding a large enough integer such that this interval between -1 over n and 1 over n is so small that it avoids any fixed x. Does this make sense what I'm doing? What I'm showing here is that no x not equal to 0 can be inside this intersection. Because if any x is not 0, I can find an integer large enough such that this interval excludes that thing. And once one of these intervals excludes x, then x cannot be in the intersection of all of these.
I have a quick question.
Sure.
So I noticed that for the union of AI, the one we did before, you wrote an interval, whereas the one directly below it, you wrote a set. So are we supposed to be writing sets for these answers or intervals, or does it just kind of depend?
So interval notation is a way of writing a special kind of set. These are special subsets of the real line. And they're very special because they include everything between one number and another number. A general subset of the real line can be much, much crazier than this. This is kind of like a very nice subset of the real line. But in any case, any union of sets or intersection of sets should be a set. So here I wrote out what the set was, and notice that here a union of intervals did happen to be an interval. What you can interpret this answer as being is that the intersection of open intervals is not necessarily an open interval. In fact, another way to write this is 0, 0 with closed brackets. So this is something to notice about intersections and unions of sets. The intersection of infinitely many open intervals does not necessarily end up giving you an open interval in its conclusion.
Okay, that makes sense. Thank you.
Yep. Yeah, so this notation is very special to working with the real numbers, and then you get these special sets that you can think about. Any other questions on this? I think this is a good example to think about. Okay, so is everyone happy with this? No further questions?
I have one question.
Uh-huh.
So for a range, is a range basically like you can think of it as a set, but it's given that every element in that range is a real number?
A range is a special kind of set. It is a subset of the reals, and it is a subset which has this nice property that it contains every number in between the two edge points.
Okay.
There are much crazier sets inside the reals. For instance, I can consider the set, consider the union of the sets 1 over I for I is equal to 1 all the way up to infinity. So this set consists of the following numbers: 1, 1/2, 1/3, 1/4. So I can make a list. This is equal to 1, 1/2, 1/3, 1/4, etc. All of these numbers for arbitrarily large things. This is an interesting subset of the reals that, of course, doesn't look anything like the intervals that we've been talking about. So really, the intervals are very special subsets of the reals. But
Okay,
there are
cool.
plenty of much weirder subsets of the reals. Does that kind of help? I'm not sure if that was actually directly answering your question, but
Yeah, no, it did. Yeah.
Yeah.
Thank you.
Yep. What does the I equals 1 mean under the intersections and unions? So the I is what's called an index set. So I here. So I is, so here, what I should really say is when we are doing general intersections and unions, we must parameterize the sets that we are unioning. The sets somehow. So what this symbol means, I equals 1 all the way up to infinity of some set AI, means that I've got one set for each positive integer. So I have a set A1, I have a set A2, I have a set A3, I have a set A4, I have a set A5. In other words, I'm parameterizing the sets that I'm unioning up by the positive integers, 1, 2, 3, 4, 5, all the way and so on. If I did a union from I is equal to 0, or I could do a union from I is equal to -1 all the way up to 40. This means that my way of keeping track of the sets BI that I'm unioning together are, I've got one set B -1, I've got a set B0, I've got a set B1, all the way up to a set B40. And I'm going to take the union of all of these things. So here, this I is telling you that I'm parameterizing my sets that I'm going to union or intersect together by some integers, basically. I could also consider, for instance, let's go back to this exact problem where the AIs are equal to 0i. I could also ask for the union from I is equal to 4 all the way up to infinity of the AI. And what's the answer here? oh, this isn't a very good problem. I should do the intersection. The intersection from I is equal to 4 all the way off to infinity of the AI.
Would it just be A4?
It'll be A4, right? Because now the first interval is the interval from 0 to 4, and then A5 is the interval from 0 to 5, and then A6 is the interval from 0 to 6, right? So the intersection of all these will be precisely the interval from 0 to 4. Does this kind of help show you what I'm doing when I'm using these symbols, the eyes and stuff like that? Yeah, it's telling you how I keep track of the sets that I'm unioning or intersecting up. Good questions, all of y'all. Any more? So what you're writing, 0 to I, you have to specify what this set is. Is this the set of all integers from 0 to I, or is this the set containing 0 and I? If you could be a little more specific, then I could answer the question. What exactly is the set that you mean when you're talking about 0, I with the curly braces? So you're saying the set containing the elements 0 and I? Okay, and then you're asking about the intersection of the sets containing 0 and I from I is equal to 1 all the way up to infinity? Yeah, then this is precisely the set containing 0. Because here, the only elements of this set are 0 and I for some arbitrary I. But of course, this is a very different question from asking something about these, where I'm asking about an interval, right? These are extremely different sets. What is the union from I is equal to 4 all the way up to infinity of 0, I? Zero will certainly be inside the union because 0 is in at least one of the sets. Well, there's no need to apologize, right? 0 will definitely be inside the union because 0 is inside all of the sets. But for a union, you only need an element to appear in one of the sets. Yes, it'll be all integers that are greater than or equal to 4, including 0. So 0, 4, 5, 6, 7, all the way up. This will be the union. Any questions on this? Zero is included because zero has this very strong property that it's inside every single set. But for a union, you don't care about whether something is in every single set, you just care if it's in at least one set. So here, if I start listing out these sets that I'm caring about here, it's 0, 4, 0, 5, 0, 6. And the only thing that matters is, does a number appear in one of these sets? Well, 0 certainly does because it appears in the first set, or it appears in the second set, or it appears in the third set. Any of these would be sufficient for 0. Then the rest of the numbers appear in exactly one set. But the union kind of doesn't know the difference between appearing in a ton of sets or appearing in just one set. Does that help, Angel? Yeah, these are great questions. There's some tricky, interesting stuff that happens with these infinite unions or intersections. Any further questions? No? Okay, 5 minutes left. Time to do all of section 2.3. Let's go. Functions. What are functions? Functions are how sets speak to one another. All right. So let's define what a function is. So we're going to actually have two definitions, one that almost always works, and one that will be the true definition that we take. So the first definition, which almost always works, is going to be the following. A function, f, from a set A, from a non-empty A to a non-empty set B, is an assignment for each element of A unique, capital a unique element of B. So what we write is f from A to B. So this line is describing what sets the function goes between. And then down here, there are several notations of describing what happens to an element. I can either write an element A maps to an element B, or I can write f of A is equal to B. Either of these are ways of saying what does the function do to elements. Question mark. Okay. Any questions on this? Now, we've all seen functions many times before, but now we're going to deal with them pretty rigorously. Can anyone who has possibly read ahead know what conditions that I have in this definition that I want to remove with a more general definition?
Non-empty set?
Yeah, I can actually remove this condition that A be non-empty with the following definition. So this is definition 1, and this is definition 2, but like version 2. Better. A function from A to B is a relation from A to B. What is a relation again? What's a relation on two sets? Relations. Yes, it has to do with the Cartesian product. A relation is a subset of the Cartesian product. Perfect. Subset of the Cartesian product, A cross B, is a relation from A to B such that for all A in A, there exists a unique element A comma B in R. So I'm calling the relation R, and so R is some subset of tuples, right? It's some subset of the Cartesian product. And what I'm saying here is for every element of the set A, I have a unique tuple that starts with that element A and has as its second element some element of B. It is 10:10, so it is time to end class. But I just want to point out the following interesting thing is that definition 1 required the set A to be non-empty. That is true, right? I've been writing the boldface R's for so long that writing a regular R feels difficult. But the point is that actually, when I'm thinking about relations, I can think about A being an empty set, right? Here's another question. What is the set, the empty set cross B for any arbitrary set B? Yeah, this is equal to the empty set. And so with this definition, this whole thing is going to be vacuous, right? I'm automatically going to produce a relation on the empty set. What is the only subset of the empty set?
The empty set.
The empty set, right. So what I can do with this definition is I can find a subset of the Cartesian product, namely the empty set, and this condition is vacuously true because there are no elements in A. So this definition allows us to extend our definition of function a little bit. We'll come back to this sort of semi-confusing way of thinking about functions on Monday. Thanks for class, y'all, today. It was good. Nice Friday discrete math class.
Thank you.
Yeah, have a nice weekend, everyone.
Thank you. Have a good weekend.
A bientôt.
For the midterm, is there going to be like a study guide, or is it just going to be like everything we've covered so far?
It's going to be everything we've covered since the last
Okay.
exam, pretty much. Yeah.
Cool. Thank you. Have a good day.
You too.